Hey math friends, this is AP Calculus section 3.2 notes. Welcome back to our journey on learning all of the different differentiation rules for all different kinds of functions. Yesterday in our notes, section 3.1, we learned the power rule and how to differentiate polynomials. We also learned that the derivative of the exponential function e to the x is itself e to the x, interestingly enough. Today we are going to talk about two rules that help us with combinations of functions. Most of the time these functions are polynomials, though they do not need to be necessarily. But the first rule, the product rule, talks about how to differentiate when two functions are being multiplied together. And this is the product rule. And the product rule says that if f of x and g of x are both differentiable functions, and you have the product of these two functions, then the derivative of f of x times g of x is equal to f of x times the derivative of g of x plus g of x times the derivative of f of x. And I like to kind of simplify this, and I say the product rule says that derivative with respect to x of f of x times g of x is equal to first d second plus second d first. So if you can remember that little saying, that's going to go a long way in helping you remember the product rule. So let's take a look at example 1. We have two functions that are being multiplied together. The square root of x is like our f of x, or our first, and e to the x is like our second. Now, remember that any root function can be written as an exponent, and then we can think of that in terms of the power rule when we are differentiating. So the first thing I'm going to do is I'm going to rewrite my function as y equals x to the 1/2 power times e to the x. I just rewrote the square root of x as x to the 1/2. So x to the 1/2 here, this is what I would call my first, and e to the x is what I would call my second. So if I am going to find y prime, I'm going to follow my little rule, which is first, so x to the 1/2, times d second. Derivative of e to the x is e to the x itself, plus second function, so e to the x again, times derivative of the first. So now I use the power rule to differentiate x to the 1/2. Bring the exponent down in front, so 1/2 x, and then subtract 1 from 1/2. Well, 1/2 minus 1 is negative 1/2. And of course, now I can clean this up and I can write it a little bit nicer. Y prime would be equal to x to the 1/2 is the square root of x times e to the x plus e to the x times x to the negative 1/2, that should be brought downstairs. It's the square root of x in the denominator, and the 2 from 1/2 is also in the denominator. So this is 1 over 2 times the square root of x. And then the last thing I could do to simplify this, since I've got two things being multiplied together plus two things being multiplied together, notice there's a common factor of e to the x. So I could factor that GCF of e to the x out, and I could write my answer as e to the x times the quantity, the square root of x, plus 1 over 2 times the square root of x. And that is how I would leave my answer. This is the derivative of y. Example 2, once again, we have two functions that are being multiplied together. So I will start the same way I started the last problem. I've got t plus e to the t times, and then 3 minus the square root of t, I'm going to write as 3 minus t to the 1/2 power. Again, thinking ahead, I'm going to be using the power rule on that, so I want that term to look like a power. All right, I know that my first in this case is t plus e to the t, and my second is 3 minus t to the 1/2 power. So r prime of t is equal to first, t plus e to the t, times d second. Derivative of 3 is 0. The derivative of negative t to the 1/2 is negative 1/2 t to the negative 1/2. So there's first d second, plus second, 3 minus t to the 1/2, d first. Derivative of t is 1, plus derivative of e to the t is e to the t. All right, and now I can do some simplifying, and I probably should. Right here, this is distributive property, and right here, this is FOIL. So if I just do some algebra at this point, r prime of t is going to be equal to negative 1/2 t to the 1/2 power, because t to the first times t to the negative 1/2 would be t to the positive 1/2, and then minus 1/2 e to the t, t to the negative 1/2, plus, and then when I FOIL, I get first outer inner last, I get 3 plus 3e to the t minus t to the 1/2 minus e to the t, t to the 1/2. And at this point, I basically only have two terms here that are like terms, and that is this t to the 1/2 term and that t to the 1/2 term. So negative 1/2 t to the 1/2 minus 1 t to the 1/2 is negative 3/2 t to the 1/2. So r prime of t would be equal to negative 3/2, and then t to the 1/2 is the square root of t. And then the second term, I would just rewrite as negative e to the t over 2 square roots of t, right? The 2 is on the bottom, t to the negative 1/2 goes downstairs, but e to the t is still on top, plus 3 e to the t, and minus e to the t, and then t to the 1/2 I would write as the square root of t. And although that looks horribly messy, that's about the best that I can do. I really can't do anything more than that. The other rule that we're going to talk about today as far as combinations of functions is the quotient rule. And the quotient rule is obviously how to differentiate when you have a quotient of two functions, something upstairs being divided by something downstairs. So it says the derivative with respect to x of f of x divided by g of x is equal to g of x times the derivative of f of x minus f of x times the derivative of g of x, all divided by g of x squared. All right, I have a little quotient rule says shortcut for you to help you remember this. Here's what the quotient rule says. The derivative with respect to x of f of x divided by g of x is equal to low d high minus high d low divided by low squared. Low d high minus high d low divided by low squared. Okay? And in most cases with these problems, do not worry about simplifying the denominator unless it's something really simple. But if it's like a trinomial, I'm not going to ask you to multiply out a trinomial times itself. Just leave it as the trinomial in parentheses squared. Okay? All right, so let's try example 3 and see how we do. Keeping in mind these are both polynomials, so they're both going to require the power rule when we differentiate them. So our x plus 1 is our high function, and our x cubed plus x minus 2 is our low function. Y prime is going to be equal to low x cubed plus x minus 2 times d high. The derivative of x plus 1 is 1. Derivative of x is 1, derivative of 1 is 0, so 1. So low d high minus high, x plus 1, d low. Derivative of x cubed is 3x squared. Derivative of x is 1, and derivative of negative 2 is 0. So 3x squared plus 1. All over low x cubed plus x minus 2 quantity squared. And again, we are not going to worry about simplifying that denominator. However, we are going to work on simplifying our numerator. So in the numerator, x cubed plus x minus 2 times 1 is just going to be x cubed plus x minus 2. And then we have to FOIL x plus 1 times 3x squared plus 1. And every term is going to be negative because of the minus sign in the middle of the quotient rule. So 3x squared times x times negative 1 is going to give me negative 3x cubed. My outers times negative 1 gives me negative x. My inners is going to give me negative 3x squared. And my last is going to give me a negative 1. And this is divided by x cubed plus x minus 2 quantity squared. And then the last thing is, can I combine any like terms in my numerator? I have an x cubed minus a 3x cubed, so that's going to make negative 2x cubed. The x's happen to cancel out. That's coincidence. Positive x, negative x cancel. Then I have a negative 3x squared, and negative 2 minus 1 gives me a negative 3. So my numerator is negative 2x cubed minus 3x squared minus 3, and that's going to be over that denominator, x cubed plus x minus 2 quantity squared. Example 4, we are supposed to differentiate another quotient. This time our high function is just e to the x. Remember, the derivative of e to the x is e to the x. And our low function is 1 plus x squared, which is a polynomial. So s prime of x is going to be equal to low 1 plus x squared times d high. Derivative of e to the x is e to the x. Minus high, e to the x, d low. Derivative of 1 is 0. Derivative of x squared is 2x. And this is all over low, 1 plus x squared squared. Okay, so now let's simplify our numerator, combine like terms, see what we get. We can distribute e to the x to 1 plus x squared, and we get e to the x plus e to the x squared minus 2x e to the x. And of course, hopefully you notice, let's finish that off, I apologize, over 1 plus x squared squared. Hopefully you notice in the numerator that we have 3 terms, and all 3 terms contain e to the x. So to simplify things a little bit, let's factor out that e to the x in our answer. So we will have e to the x, and then our first term will be a 1. Our second term will be an x squared, and our third term will be a negative 2x over 1 plus x squared squared. And if you're really feeling like you want to be an awesome math student, you can rewrite that numerator with those terms in the parentheses in descending order. So x squared minus 2x plus 1 divided by 1 plus x squared quantity squared. Of course, that last step gives you bonus points in my eyes, but certainly the step before it, when we had e to the x times 1 plus x squared minus 2x over 1 plus x squared squared, still totally correct. I just see a polynomial and I want to put it in descending order. In example 5, our last example, it says above it, note, don't use the quotient rule every time you see a quotient. Sometimes the function can be written in the form of a polynomial, which is simpler in terms of differentiation. And that is the case that we have here in example 5. Please note that our denominator right here is a monomial. So it would actually be simpler to divide every term in the numerator by our monomial denominator, turn this into a polynomial instead of a quotient, and then use the power rule to differentiate. So I'm going to show a step here that you may or may not need to see, but just to make sure that we're clear on what we're doing, I'm taking every term in my monomial, or in my numerator, 3x cubed, I'm dividing it by x squared. So minus 2x squared over x squared plus 4x over x squared and minus 7 over x squared. If you can do this step in your head, that's wonderful. So what I really have for y is going to be equal to 3x minus 2 plus 4x to the negative 1 minus 7x to the negative 2. And notice that I'm writing my last two terms with negative exponents in the numerator because when I differentiate, I'm going to use my power rule, so I want to see those as exponents upstairs. So now my y prime is going to be equal to the derivative of each term using the power rule. The derivative of 3x is 3. The derivative of negative 2 is 0. The derivative of 4x to the negative 1, I bring the negative 1 down, multiply it by the 4, so that's going to become negative 4x to the, subtract 1 from the exponent, it becomes negative 2. And then my last term, negative 7 times negative 2 makes positive 14. And then when you subtract 1 from the exponent, it becomes a negative 3. So y prime is equal to 3 minus 4 over x squared plus 14 over x cubed. And we did not use the quotient rule even though we started with a quotient, again, because our denominator was a monomial. But now let's take a look at what this problem may have looked like if we had attempted it using the quotient rule so that we can compare and contrast the amount of work here. So over here, what if we use the quotient rule? We should still get the same answer as long as we do our math correctly because this is a quotient. So my y prime, again, quotient rule is low d high minus high d low over low squared. So y prime is going to be equal to low, which is x squared, times d high. So I have to take the derivative of each term in my numerator, which is going to be 9x squared minus 4x plus 4. Then minus high, so 3x cubed minus 2x squared plus 4x minus 7 times d low. The derivative of x squared is 2x. And this is all divided by low, which is x squared squared. And now I need to do some simplifying in my numerator. Lots of slow, careful algebra here. First, I'm going to distribute x squared to that trinomial. So that's going to give me 9x to the 4th minus 4x cubed plus 4x squared. And then in the second part, I have to distribute the 2x to that 4-term polynomial, but I also have to distribute this negative 1 right here that comes from the quotient rule. So I'm going to do both things at once. 3x cubed times 2x is going to give me 6x to the 4th times the negative 1, so negative 6x to the 4th. 2x times negative 2x squared is negative 4x cubed times a negative 1 is positive 4x cubed. 2x times 4x is 8x times negative 1, 2x times 4x is 8x squared times negative 1 is negative 8x squared. And then finally, 2x times negative 7 is negative 14x times negative 1 is positive 14x. and this is all divided by, in the bottom, x squared squared, we can rewrite as x to the fourth. Okay, now in the next step, we should try to combine any like terms that we have in our numerator. So I'm just going to go term by term. I have 9x to the fourth minus 6x to the fourth. So that is going to give me 3x to the fourth. I have negative 4x cubed and positive 4x cubed, so coincidentally those cancel out. I have positive 4x squared and negative 8x squared, so that's going to give me negative 4x squared. And then finally I have that plus 14x, and this is all divided by x to the fourth. So now in my last step, I'm just going to divide each term by x to the fourth and rewrite my answer as a polynomial. 3x to the fourth divided by x to the fourth is 3. Negative 4x squared divided by x to the fourth is going to give me negative 4 over x squared. And then 14x divided by x to the fourth is going to give me positive 14 over x cubed. So as you can see, I did get the same answer using the quotient rule as I got when I divided everything by x squared first and then used the power rule. But I think you will agree that number one, the power rule was easier, and number two, there was a lot less chance for error with that method than there was with the quotient rule. I had to do so much more algebra when I did the quotient rule, and there were a lot more opportunities for me to make an error either with my signs or with my combining like terms or with my dividing. So when you're dividing, when you have a quotient, before you dive into the quotient rule, if your denominator is a monomial, consider simplifying first and turning your function into a polynomial and using the power rule rather than diving right into the quotient rule.